Over the last few videos, we have been talking about the behavior of the common emitter amplifier circuit. In particular, in the last video, we talked about the calculation for the gain of this amplifier, at least when the signal Vs was small. And just to remind you, when we are talking of small signal amplifier behavior, we are essentially treating a linearized version of the nonlinear transistor, essentially using H parameter equivalents or effective small signal models, which allow you to use superposition principle. So when you are talking of the effect of Vs, you can treat VCC, the DC bias voltage, as 0. Of course, when you treat the DC bias voltage as 0, then this point gets connected to the ground, which makes R1 come in parallel to R2, RC joining the collector to the ground, and you have RE right here. So basically this is your AC small signal effective model. What we have done here is we are assuming this is the mid-band behavior, that is, the frequency is high enough for the three capacitors that you can see, the CB1, CB2 and CE, all three to have small enough impedances. Remember, the impedance of a capacitor goes down with frequency. So we are talking of frequencies which are high enough at which these capacitors can behave like shorts, which means this is directly connected. So is this. So RC and RL effectively are in parallel and RE is shorted out. So this is what your AC small signal amplifier circuit is, specifically for the mid band. This is not the AC small signal amplifier circuit, this is the mid band version. Just to remind you, if you go to very much higher frequencies, the parasitic capacitors which are there across the junctions in the transistor, they will now start to pick up and modify the behavior of the circuit. So we are in some middle frequency range which is high enough so that you can treat the blocking capacitors and the emitter bypass capacitor as shorts, but not so high that the impedance of the stray capacitances or junction capacitances in the transistor, they become sufficiently small to affect the circuit. Now, notice that although RC and RL are actually in parallel, I have not written down them as a parallel combination here. I have deliberately displayed RC and RL as separate. This is to emphasize the fact that everything that you see within the yellow box here is actually the amplifiers, or at least the small signal AC part of the amplifiers. On the outside you have the source in series with the source resistance on this side. On the other side, on the output side, you have the load resistance. So all this in yellow is inside the amplifier, these two parts are outside, and this helps us talk about how the amplifier looks like from the point of view of the external world. So we are next going to describe an effective model for the amplifier as far as the source and the load is concerned. Note that I am saying this is an effective model for the amplifier, not an equivalent model, and there is a reason for this distinction in terminology, and I will explain soon. But first, let's take a look at the effective model. Notice that as far as the source is concerned, whatever is on this side essentially is something which takes current away from the source. So the source doesn't really care what happens to the current which it delivers after it goes into the amplifier. All the source sees is that something is taking away current from it. So as far as the source is concerned, the amplifier, in fact not only the amplifier, the whole part beyond this point, that is the amplifier as well as the source load resistance, all of these together, they look to the source effectively like a single impedance connected across it, and this impedance is called the input impedance which the source is going to see. Well, what happens from the load side? The load side is slightly more complicated because on the load side you basically have a voltage source which is not an independent voltage source. It's a voltage source which is proportional to whatever input is given. That's the amplifying action. But as in all voltage sources, it's not going to be just a voltage source, it's going to be a voltage source in series with the impedance, which the load is going to see. And this impedance, which you see on the output side, is what is called the output impedance. So the effective circuit for the amplifier looks like this. Okay, so this triangle shaped thing is a standard symbol which is often used for an amplifier, and it's meant to look like an arrow which points to from the input to the output. And if you focus on the input side, you have VSRS here, and what it sees is essentially an impedance Zi, the input impedance, and this voltage is Vi, the voltage which the amplifier gets to see. Note that it's not exactly equal to Vs because of the potential division across a series combination of Rs and Zi. On the output side, what RL sees is this quantity, this controlled voltage source, in series with an impedance ZO, the output impedance. Okay, what is this controlled voltage source? It's AVO Vi. Well, it's basically output voltage divided by input voltage. Input voltage, note, not the source voltage. So this is output voltage by the input voltage, but the O here, up here, really signifies a special thing. Notice that the output voltage will not be AVO Vi in general, right? Because again, the output voltage will be divided between ZO and RL. So AVO is actually VO by Vi only when RL is infinity or the output is open. If the output here is open, only then do you get the voltage gain to be AVO. So that's the O here. The O here signifies this is the output voltage by the input voltage ratio, but when the load is open or RL is infinity. Now, why do I say that this is an effective circuit and not an equivalent circuit? For this, you have to understand exactly what an equivalent circuit means. I've said this before, but let me repeat this once again. An equivalent circuit for, say, a two-port network would be something which, if you were to replace the two-port network by, would keep voltages and currents everywhere else the same. That's fine. But on top of that, the details of the equivalent circuit will depend only on what is inside the amplifier, not on what is outside it. Which is why once you create, say, an H-parameter equivalent circuit for a two-port network, after that you can happily keep on connecting different sources to it on the input side, different loads to it on the output side, and you can still keep on using the same H parameter or Z parameter or Y parameter equivalent circuit. Here the situation is not really like that. The Zi here essentially captures what the source sees, which is not only the amplifier but also the load resistance. In fact, the Zi could very well depend on the load resistance, and usually it will. Similarly, when you are looking at it from the load side, whatever it sees depends not only on the yellow box here, but also on what is on this side. So, the parameters that you will see, ZO and AVO, they may depend on the source resistance, not just on whatever is inside the amplifier. This means that while these parameters, Zi, ZO, etc., are good things for explaining the behavior of the circuit, and we will soon use them to explain the behavior of the circuit in a big way, they are not really equivalent parameters for the simple reason they depend on other things. The Zi depends not only on whatever is inside the amplifier, it also depends on RL in general. ZO also depends on RS. So, frankly, if you were to change the source, you would have to change the value of ZO that you use. Or if you change the load, you would have to change the value of Zi that you use. This is why I am distinguishing this from an equivalent circuit. Very often this distinction is not made in textbooks, but that often leads to confusion. Okay, but let's just say for a particular source load connection, we have actually calculated the ZI, ZO and AVO. How to do that? We are going to describe that soon. But let's just say we have the values of ZI, ZO and AVO available. Can I use this to calculate the gain that I want? Okay, that depends on which gain do you want. But very often the gain that you want is VO by VS, the output voltage by the source voltage. So now let's take a look at AVS. And okay, first of all, notice that the input voltage that the amplifier is going to get, VI, is really not VS. It's the series potential division between ZI, which is the impedance that the amplifier presents to the source, and RS, the source's own impedance. So this is the extra factor that you get which connects VI to VS. On the other hand, the output voltage is not AVO VI, it's RL by RL plus ZO into AVO by VI. Again, it's because the output potential voltage is divided between RL and ZO, and what goes across RL is really the output voltage. So putting these two things together, what we see is AVS, this ratio, VO by VS, has two extra factors beyond AVO. AVO, remember, is the voltage gain, VO by VI, when load is infinite. But in addition to that, you have two extra factors. One is RL by RL plus ZO, which is the factor which is coming because of the potential division on this side. The other is ZI by RS plus ZI, which is what is coming from the potential division on the other side. Now, let me point out that there is a slightly different way of writing this, which is AVS is written in this form. That's simple. You are just divided by the numerator. But the reason why I am emphasizing this form is this. If RL and RS are external factors, they depend on whatever load or source you are connecting to the amplifier. Now, if ZO is very small compared to RL, this statement that I have made here, and ZI is very large compared to RS, what is going to happen is that both of these factors are going to approach their maximum value of 1, which means AVS will be given by AVO. Now, you might think that the reason why I want these two conditions, ZI, the input impedance will be much bigger than the source resistance, and ZO, the output impedance will be much smaller than the load resistance, is because that ensures that the gain AVS, the VO by VS ratio, is the largest when this happens. However, the situation is a bit more subtle than that. We are not really that interested in getting the largest possible value for AVS. In an engineering scenario, what is much more important is to have control over your output rather than have a large output. Of course, you may want a large output, but just having a large output which fluctuates all over the place is no good to anybody. So, what you really want here is to ensure that your amplifier will basically behave the same way, produce the same kind of gain, irrespective of what kind of load or source you are using. So, if the input impedance is much bigger than RS, then the actual value of RS, whether it is 10 ohms or 20 ohms or 50 ohms, doesn't matter if ZI is of the order of, say, tens of kilo ohms. Similarly, if ZO is of the order of, say, a few ohms, then whether RL is a kilo ohm or, say, 500 ohms will not really matter much. The gain that you will ultimately get will stay more or less the same. It is this independence from external factors that is the reason why we demand ZI to be very huge and ZO to be very small. In fact, the better these conditions are met, the better the amplifier is going to be. Well, just one clarification here. Here we are looking at this amplifier as a voltage to voltage amplifier, something which takes in a voltage and produces an output voltage. And because of that, we need these conditions. A good voltage to voltage amplifier should have a high input impedance, ideally infinite input impedance, in which case I will completely ignore whatever RS is, and a low output impedance, again ideally a zero output impedance. Even though ideal situations are not usually met in the real world, you can get pretty close to them by at least ensuring that Zi is much bigger than whatever RS you're expected to connect. So this is the demand that we make when we are talking of voltage to voltage amplifiers. Of course, if we are talking of other kinds of amplifiers, like say current to current or current to voltage or voltage to current amplifiers, the kind of amplifier you're talking about essentially depends on what you want your amplifier to do. These demands would very well change. The demand of a huge input impedance and low output impedance, let me stress once again, is for voltage to voltage amplifiers. With this background, let us now try to calculate the three quantities Zi, Zo and AVO for our CE amplifier. In the last video, we had actually already demonstrated how to calculate AV, the voltage gain, for the CE amplifier for the same circuit, but there we use the full H parameter equivalent for the transistor. Today we are going to take a simpler route. We are going to make life a bit simpler for ourselves by essentially starting with the CE amplifier. Remember, this is not the full CE amplifier circuit, this is just the mid-band AC equivalent, and then we will replace the transistor not by the full H parameter equivalent. We could do that, but it's going to only make the calculation a lot more difficult. We are going to replace it by the approximate effective model. You could say that what we are doing is we are actually using the H parameter model with the approximation that HRE and HOE are both 0, because they are tiny really for most NPN transistors. Or we could just use the Ebers-Moll physically motivated model in the approximate AC sense to arrive at the equivalent model, which is the same essentially as the one that I talked about right now. So let's see what happens if I do that. So this is the circuit that we are dealing with. Note that this is essentially the same circuit as the one up above. All we have done is replace the transistor here by this Ebers-Moll approximate model, beta plus 1 RE resistance here and beta IB a current source here. And this is of course the emitter lead. So all I have done is just connected the effective equivalent circuit, approximate equivalent circuit to transistor. I am showing that this point is at a voltage Vi and this point is at a voltage Vo. Let me just point out that when I say this point is at a voltage Vi, what I really mean is that the voltage is Vi between this point and the ground. Similarly, this point, this Vo is really the voltage between this point and the ground. Okay. Now, what we do is we try to calculate Zi. So Zi is the impedance which you see looking in from these 2 points. Now, for this particular circuit, especially because we are using the simplified H parameter model, the calculation of Zi becomes almost trivial. What does the source really see? Or what do you see between these 2 points? You get to see a resistance which is R1 parallel R2 connected between these 2 points. And we also see a beta plus 1 RE resistance essentially connected between these 2 points. Just to remind you, beta plus 1 RE within the approximation that we have made is the same as HIE. But anyway, we are calling it beta plus 1 RE, which is physically beta motivated. RE, remember, is the emitter diode resistance, and beta plus 1 is a extra factor that you get. So notice that all the Zi that you have, all the resistance you see between these 2 ports is simply a parallel combination of this resistance and this beta plus 1 RD. So this is all that you see. And that's all that Zi is. So Zi comes out to be simply this quantity R1 plus R2 parallel with beta plus 1 RD, which of course is HIE for the transistor. Well, just a word about the typical sizes involved. Typically in most circuits R1, R2 would be tens of kilo ohms, whereas HIE, beta plus 1 RD, would be of the order of a kilo ohm or so. Just to remind you, RD is a diode resistance effectively, so it's of the order of 26 millivolts by the bias current, capital I. So the capital I is of the order of few milliamperes, small RD is of the order of tens of ohms, but beta is of the order of 100, so HIE, the product of beta plus 1 times RD, works out to be around a kilo ohm or so. So in most cases, if you put a kilo ohm in parallel with R1, R2, which are of the order of tens of kilo ohms, you would end up effectively, approximately getting HIE again. So this is, though this is not exact, but approximately this is the same as HIE. Now hold on a minute. Remember I made this song and dance about what we have being an effective circuit and not an equivalent circuit. Why? Because Zi depended not only on what was inside the amplifier, but could depend also on what was outside, namely the RL. Note that this expression for Zi does not have the RL in it at all. It depends only on R1 parallel R2, which is the resistance, part of the resistances which are inside the amplifier, and this HIE, which is a parameter which deals with the transistor, again something which is inside the amplifier. So what happened to this big thing that I made about Zi possibly depending on RL? Well, this particular Zi, this calculation that I have done, does not depend on RL. True. But that's because we are using an approximate model for the transistor. We are not using the full H parameter model. If we had, and I will demonstrate that a while later. If we had used the full H parameter model, the result would depend on RL. Weakly, because as we have stated, this is a reasonably good approximation to the full H parameter model. But still, there will be an RL dependence. You just don't get to see it here because of the extreme simplicity of the model that you are using. Okay, now let us come to calculation of AVO, the output voltage gain. How do you calculate AVO? Remember, AVO is simply VO by VI. So the ratio of these two voltages in green that we see here. But in addition to that, you have to realize that the O in the AVO essentially means that the load resistance is put to infinity. There is no load. So we get rid of RL. So the circuit actually becomes even simpler. So now the calculation essentially is very simple. VO, notice that this current essentially has to go through RC. There's nowhere else it can go. So VO is simply beta IB times RC with a minus sign. Just note that the current is going up here and VO is the voltage at this point. So VO is minus beta IB RC. And what about VI? To find out VI, again in terms of IB, it's easiest to just go from this point to the ground using this path. And then you will see VI is beta plus 1 RD times IB. So these are the two results that you get. VO is minus beta IB RC. Of course, when load is open, if RL had been connected, RC would have come in parallel with RL in this expression. But right now we are calculating AVO. So RL is infinity. So VO is minus beta IB RC. And VI, which is same as VBE, is beta plus 1 RD, the resistance, again just the HIE into IB. So if you divide the two, you immediately get AVO. And you get a formula for AVO which looks like this: minus beta by beta plus 1 RC by RD. And if you recall that beta by beta plus 1 is actually alpha, a number which is pretty close to 1, AVO works out in minus alpha RC by small RD. So just to give an idea about the size of this, alpha is of the order of 1. RC of course depends on your biasing circuit, but typically could be a few kilo ohms and RD is of the order of tens of ohms. So this would sort of ensure that your gain in the midband would be of the order of 100 or so. It's always a good idea to have a rough notion of the sizes involved of the various quantities. So this form actually gives you the advantage that small RD can be sort of figured out in terms of the bias currents. So you can estimate what ABO is going to be for a given transistor amplifier. Okay, now that we have this, let us go on to calculation of ZO, the other parameter. We already have ZI and AVO, now we want ZO. And just before we go on to calculate ZO, let me remind you that we had actually calculated AV in the last video, where we had used the full H parameter expression. So the already first expression came out to be a bit more complicated than this. There were two reasons for that. One is we were calculating AV there, which is VO by VI, and the load was very much connected in. So instead of RC, you actually had RC parallel RL, but that's a minor complication. The other issue, of course, was that we were using the full H parameter effective model. So instead of just HFE, which is the same as beta, and HIE, which is just beta plus 1 RE, we were using HRE and HOE as well. But if you look back at that video, you will find that when we approximated the H parameter equivalent by setting HRE and HOE to 0 or negligible values, we did recover essentially this same expression with RC being replaced by RC parallel RL. That replacement is simply because we were not talking about AVO there, we were talking about AV. So while you may end up seeing various expressions for the voltage gain, and that may be confusing, you should always clearly think about which voltage gain we are talking about. Are we talking about VO by VI? If we are we talking about VO when the RL is connected, or as in this case where the RL is not connected? Or are we talking about VO by VS? And once you keep these questions straight in your mind, the confusions should go away. Okay, now let's get to the calculation of ZO. How would you calculate ZO? Now, there is a bit of a conceptual stumbling block here. If you go back to the effective circuit, this one, you would easily see that ZO is the impedance which the output port would see. Not really. The output port doesn't see ZO. It sees ZO in series with AVO-VI, but it would see ZO as the impedance connected between these two terminals if AVO-VI, this source, were 0. Okay, so that is something we have to keep in mind. Now, how do you make AVO-VI 0? Well, AVO depends on the amplifier, so unless you drastically change the amplifier itself, which of course you don't want to do, AVO will not be 0. Of course, if AVO were 0, then your amplifier would no longer be an amplifier. But it is possible to make VI 0. Why or how? Simply by making VS 0. If you short out VS, but of course keep the RS in, then VS becomes 0, VI becomes 0. So you have a situation where AVO-VI vanishes. So that is the case where you would find the output impedance to be just the impedance seen from the output terminal. What is the impedance seen from the output terminal? Well, if you can just look at the circuit and find out the impedance, that's fine. Otherwise, it's again easy. It's just the voltage seen at the output terminal divided by the current going in. But that is where the conceptual stumbling block comes in. If the input voltage is 0, so will the output voltage be. And in fact, all the currents everywhere in the circuit will vanish. So the output voltage will be 0, the current flowing into the amplifier from the output side will also be 0. And the ratio that we want here will simply become 0 by 0. Of course, something which we don't really want to calculate, or we don't even know how to calculate. But this is where we can be pretty ingenious, and we can do something which we would usually never do in real life. This is something which we do in a calculation. in real life it may be a pretty bad idea to stick a source on the output side of an amplifier. You never know, the source might burn up, the amplifier might simply burn, or something more catastrophic might happen. But in thought or in calculation, nobody is preventing you from connecting a source or voltage source across the output side. So what we will do is we will short the input, replace the RL which is outside the output port. What we do is replace the RL by a source and then ask how much current is going to be delivered by that source. So let's see how this works. So this is the same circuit as the one above, except for the fact that Vs has been shorted out, and on this side, instead of the output load, what we have done is we have connected a source Vx. I want to find the current Ix from there, and once we have the Vx Ix ratio, that will give me 0. Well, actually in this case again the calculation becomes way too simple, simply because of the simple approximate circuit we are using. Once again, if you use the full H parameter equivalent, the calculation would be slightly more complicated. But notice that whatever Ix comes in here gets divided into two pieces. One goes through this, the other goes through RC. But this current is beta IB. And how much is IB? Well, you can find out IB by looking at this side of the circuit. And it's very easy to convince yourself that because there is no source voltage here and there is no other source anywhere, for this approximate version at least IB must be 0. And if IB is 0, okay, if you don't want to take this physical argument, all you need to do is take a look at the Kashaf Voltage Law used for this loop perhaps. This is basically going to tell me that there are 3 resistances in parallel, R1 parallel R2 parallel RS here, and a beta plus 1 RE connected here. And there is no voltage source anywhere in this loop. And if you just use Kashaf voltage law, you are going to get IB equals 0. But I would say, just looking at the loop and figuring out that the current must be 0 because there is no source to cause the current is a good enough argument. But what happens when IB is 0? This path essentially carries no current, so this is open. So I don't even have to calculate Vx by Ix in this case. I know that all that you are going to see from the output side, from this ZO, is simply this RC, because this part carries no current. So the output impedance is simply RC. Okay, let me just stress one thing. I deliberately broke up RC and RL into two pieces and did not consider them in parallel at the beginning when we talked about the AC equivalent circuit. And the reason for that is to emphasize that RC is inside the amplifier. So when you are looking in from outside the amplifier, RC will be seen. RL is outside. This distinction is important when you are calculating the output impedance, because you want to figure out what the output sees, and you have to be clear about what is outside the output terminal and what is inside the output terminal. Now, having said that, once again you see that the final result here, ZO, does not depend on RS. But let me emphasize once again, that's because of the extreme simplicity of the model we are using. If you use the full H parameter model, which you will do in an assignment, you will find that ZO will actually depend on RS. Okay, so these are your final results. Again, the final results for this simplified version. Zi is R1 parallel R2 parallel beta plus 1 RE. ZO is simply RC. Okay, maybe I need to write this a bit more clearly. And AVO is minus alpha RC by RE. So what is AVS? AVS essentially is this AVO factor minus alpha RC by RE times a factor because of the voltage division in the load side. This is really RL by RL plus ZO, but ZO is RC, so I have just replaced that. And on this side you have Zi by Zi plus Rs. I've just kept Zi because I just didn't want to write this complicated expression here. And just to remind you, this factor is really VO by VI. This really is the VI by VS ratio. Remember, this is VO by VS. That can be of course thought of as VO by VI times VI by VS. VI by VS is just this potential division ratio, Zi by Zi plus Rs. But this factor is essentially the gain that we had calculated in the last video. And that did work out to be minus alpha RL prime by RE. At least once we made the approximation that HRE and HOE are negligible. There we ended up with minus alpha RL prime by RE, and that's exactly what we are getting. Notice that RC RL by RC plus RL here is exactly RL prime. So whatever we have calculated today is consistent with whatever we did in the last video. We will next illustrate the calculation of the input impedance, but this time with the full H parameter equivalent. The only reason I am doing this is to emphasize or stress that this song and dance that I made at the beginning about the effective amplifier circuit versus the equivalent circuit is actually something that you do see when you do a full, more precise calculation. So here what we have done is we have essentially taken the same circuit as before, the same circuit that we used to calculate the Zi for. The only thing is we replace the transistor, which is basically whatever is inside this red circle here, not by just HIE and HFE IB. We did call that beta plus 1 RE and beta IB earlier, but that's the same as HIE and HFE IB. But we also have included HRE VCE and this admittance HOE, which I have written down as the impedance 1 by HOE. So we are actually trying to do the calculation with the full H parameter model here. And in order to ease the calculation, what I am going to do is, what we really want is this impedance Zi between these two terminals. But I am going to first calculate this quantity Zi prime, which is the impedance between these two terminals. Why am I doing that? Because basically Zi prime is simply going to be this voltage Vi, which is also VBE, the same as the base emitter voltage. Remember, these are all AC fluctuations, not the actual base emitter voltage, but just the AC part, the fluctuation from the quiescent point values. That is true for all the things that we have calculated today, all the voltages and currents. But this, if you take this VBE, divide that by IB, you get Zi prime. Now, once you have Zi prime, Zi is trivial because Zi prime effectively looks like an impedance connected here. And Zi, the impedance connected between these 2 points, is nothing but Zi prime in parallel with this R1 parallel R2 combination. So that's all there is to it. Okay, so how do I calculate Zi prime? Well, let's make a start. First, notice that to calculate Zi prime, what I need is Vi by IB. So for that, what I'm simply going to do is write down Vi, and that's HIE-IB, the voltage drop across this resistance, plus HRE-VCE. What we need to do is write down VCE in terms of IB, and we are done. But that's actually pretty easy to do. If you look at the output side, you have a current source HFE-IB, and that drives the current through this parallel combination of 1 by HOE, RC and RL. So VCE, the output voltage, which is also VO of course, is, apart from a minus sign, just this current into the impedance. The minus sign comes in once again because the current is being driven this way, and VO is the voltage between this point and the ground. So what you get is minus HFE IB into 1 by HOE parallel with RL prime. RL prime of course is just the parallel combination of RC and RL. So now that you have this, of course this is simply minus HFE 1 by HOE into RL prime by 1 by HOE plus RL prime. So it just works out to be RL prime by 1 plus HOE RL prime times IB. This result, by the way, should be pretty familiar from the last video. We had actually used this to calculate the voltage gain that time, simply by dividing VCE by VI. Right now what we want is VI by IB, and for that what I will do is simply take this expression and plug it back here. So you get HIE minus HRE HFE RL prime by 1 plus HOE RL prime whole into IB, and that's what gives me my ZI prime. ZI prime is a ratio between VI and IB, so ZI prime simply works out to be this quantity. Okay, so let me just rewrite this to show you what ZI prime is. Just divide the VI by IB and you have got ZI prime. Well, just to make a connection with what we have already done today, HRE, as we said, is a pretty tiny quantity. So this whole thing is going to be negligibly small for most situations, unless RL prime is huge, which usually it won't be. After RL prime is bounded by RC, it cannot be more than RC. It's a parallel combination, remember. So since RC is of the order of a few kilo ohms, no matter what RL you connect, RL prime will be at best of the same order, and HRE HFE is a pretty tiny product. So this means that even if RL prime is of the same order as HIE, because of the presence of this HRE HFE, which typically is of the order of 10 to the minus 3 or less, this is for most situations negligibly small compared to HIE. So this is approximately at least HIE, or the expression that we had used earlier, beta plus 1 small re. Remember, they are both one and the same. Now that we have ZI prime, how do you get ZI? You just take the parallel combination of ZI prime with R1 parallel R2, and if you are using the approximate version, you are going to get back the original result, beta plus 1 RE parallel R1 parallel R2. When I say original result, I mean the result that we had derived at near the beginning of this video. That of course was derived under the approximation that HRE and HOE are negligibly small. So even if we do the full calculation and then neglect HRE, HOE, we are going to get back the same result, as can be seen clearly. But notice that unless we make that approximation, ZI prime depends on RL prime, which depends on RL. So strictly speaking, ZI, the input impedance, does depend on RL. So what I said about this really being an effective circuit and not an equivalent circuit parameter is actually precise, though the distinction, at least in this case, is really not that important. We will next talk about the frequency dependence of this amplifier circuit. Remember, we said that once the frequency is large enough, the blocking capacitors and the emitter bypass capacitors behave like shorts, and on the other side, the stray capacitors still behave like open. So you don't see any effective capacitance in the circuit. And because this happens over a reasonably large frequency range, we get a large mid-band region where the gain is more or less flat with frequency. It does not change much with frequency. But if you go to low frequencies, of course, the effect of CB1 and CB2 and CE are going to be important. And when you are going to go the other way, to very large frequencies, the stray capacitors are going to become important. So we will next take a look at what or how to handle the behavior at low frequencies and high frequencies. So the frequency dependence of a CE amplifier output is our next topic.